sometimes called fault current controller. And in this device, we have an AC excitation, well, the current flowing through an AC coil, and there is another coil that's maintaining a DC field. Now this could be a superconducting magnet, just supplying a DC field, and what this does is it saturates the core. So if the core is completely saturated by the DC field here, then the AC field sees no impedance due to this magnetic circuit here. Now if we have a fault current, what happens is the field due to the fault current will oppose the saturation, and it will drive the core out of saturation. If we drive the core out of saturation, then that presents a higher impedance to the fault current. This design is also used by Z Energy. If we look at the VEH characteristics, the operating point would be out here where the core is saturated. So under normal operation, there would be won't be any impedance. And now we have a fault current. The field will drive the core out of saturation, pushing us back down here, where we would have suddenly a greater impedance to the fault current. Okay, and I just want to set this up. This problem actually has symmetry about the central axis and also about this axis here. Some of the previous problems we looked at also had symmetry, but for illustrative purposes, I modeled the entire thing. Now this one is going to actually take a bit longer. So I want to show basically how to set that up. So look at the geometry. In this particular case, we are looking at the corner of this configuration here, this bit that's surrounded by the red box. Okay. Now if I want to, I can put a primary coil here and model a DC current through it to saturate the core. And now the field in the primary is going to drive the core out of saturation, presenting a higher impedance at this particular location here. So I just wanted to illustrate how to set up. In this case, this is the air region. Permeable spelled with the E, the primary. And now in this particular case, we can model a DC field by supplying a tangential H here. So if I give this a tangential H, this will give us a DC flux that's maintained throughout the circuit here. Okay. As well, the symmetry, where I've cut this through the horizontal plane, we want to make this a plane of zero tangential field. And for the Y symmetry, where we've cut it, this should be a plane of zero vector potential here. Okay. As well, we can maintain a coupled circuit, and I had a ramp sine function through these as well. Now, once again, these particular designs involve superconductors, but we're not driving the superconductor normal as we did in the case of the inductive fault current limiters. The superconductor is just used to maintain the coil in saturation, the permeable region in saturation. As well, the primary coil won't necessarily desaturate the entire circuit. We would just be looking at desaturating a smaller region of the circuit here.